All right, welcome. In this video, we're going to take a look at a self-balancing binary search tree called an AVL tree, also known as an Adison-Velskii-Landis tree, named after the researchers, the Soviet researchers who invented it in 1962. Now, as I mentioned, this is a self-balancing binary search tree. This is also going to be one of our first examples of a self-organizing data structure. This is a data structure that's going to reorganize how it stores the data inside of it to, well, suit some purpose. In our case, we're going to try and keep our depth pretty small, and the sort of side effect of that is to keep the operations that we perform on the tree efficient, as efficient as possible. So again, we commonly call these an AVL tree. Now an AVL tree is also a binary search tree. So in the last couple videos, I talked about what a binary search tree is and some of the basics of a binary search tree. And we can see here that this example tree is indeed a binary search tree. It's one that we were looking at in the previous video. And remember that a binary search tree is defined by the elements in the left subtree must be less than the value of our node, and then the elements in the right subtree should be greater than the value of our node. So again, verify for yourself that this is true for all the nodes in this tree. So this satisfies the binary search tree part. And now we're going to talk a little bit about how we can add the principles that Adison-Velskii-Landis added, like I said, in 1962. Okay, so the first thing that they're going to do is they're going to give us a criteria through which we're going to determine if our binary search tree is balanced or not. Now, we already, when we were looking at heaps, looked at an idea of what it means to be sort of completely balanced or have a complete binary tree. Those are sort of the best structure you can get if you're looking for something that's squat and what we might call balanced. Now, when it comes to binary search trees, there might be more than one way we can define balance for the tree, and we might characterize a particular structure as being balanced or not. Now again, when we were looking at heaps, maybe let's just take a look at a quick example here. When we were looking at heaps, we said, well, we want to make sure that we can have heaps of different sizes. So, you know, here's a heap of size 3. It also happens to be a complete binary tree of size 3. We noticed that the next complete binary tree with all the nodes in it would be of size 7. And since we might want to allow for trees of size between 3 and 7, 4, 5 up to 7, we should allow that maybe this bottom level here, maybe we could eliminate some of our nodes. So, you know, maybe that node's gone, and technically maybe that node's gone too. Remember, we talked about left loaded, maybe keeping everything on the left. But then maybe this here should count as also balanced. That's true for our heaps. Now, for our binary search tree, we might want to consider this balanced as well to allow us to have the opportunity of having 4 nodes. And that might allow us to have other ideas of what might balance be as well. This might be a balanced shape as well. So we want to consider different definitions of balance, and Adison-Velskii-Landis came up with one definition of balance where they said, okay, what we're going to do is we're going to rely on this height calculation, and we're going to look at the height at the left child, and we're going to calculate the height at the right child, and we're going to calculate the difference. So we're going to call this the balance factor. We're effectively just taking the difference to try and see, well, okay, which side is heavier. If this difference is 0, that kind of represents balance. If it's not 0, then the magnitude, the absolute value, is going to tell us how imbalanced we are. And then the sign is going to tell us which side is in balance. So if we're doing left child minus the right child, then if we end up being minus, high in the negatives, then that means the right side must have been heavier. And if we end up in the positive, then that means the left side must be heavier. Okay, so we're going to use that, and I've actually done that already for this tree here, and we can just verify. I've also got the note here in case you have forgotten. The height of a node is the distance from the node to its deepest leaf. So actually, when I start labeling a tree like this, if I just started this tree as I had when I was building these slides, I would start labeling at the bottom, because the leaves are the easiest ones, since the distance from the leaf to the deepest leaf, well, is itself, so the height is 0. I'm counting edges here. So this would be 0. So all my leaves, you'll notice, have height 0. Also, since all our leaves have no left child and no right child, the height of the left minus the height of the right is 0. They're the same. The height of the left and the height of the right are the same. And so their balance factors are all 0 as well. So this is an easy case. One thing I remember whenever I'm attacking an AVL tree, I say, oh yes, okay, all the leaves have height and balance factor of 0. That's sort of like an initialization case, if you like. In fact, we could use maybe a recursive algorithm to calculate these, and if we were, this would be the terminating case. We would terminate when we get to leaves or maybe to null, which raises the next sort of interesting question for me, which is, you'll notice here that since I'm counting edges, I've actually got a 0-based height. I tend to prefer 0-based heights in most of my calculations and depths. Usually it makes the math work out nicer. But when we use a 0-based height here, one consequence of that is then the height of the empty, the child that we're looking at here is empty, it's null. The height of the empty child, or the null node, must be -1, not 0. Okay. On the other hand, if we we can do this calculation. Nothing in this calculation says we need to use 0-based calculations. We could use a 1-based calculation now, and that would allow us to have our nulls return zeros. Okay, we just need to be sensitive of that. Remember, there's nothing really difference between our 0-based and our 1-based height calculation other than a +1 or a -1 when converting one to the other. Okay, but we'll be sensitive of that when we're considering our calculations here. All right, so I started with the leaves. I said they're all going to be zeros. Well, then if we're going to calculate for a non-leaf node its height, let's start with its height. Again, we can think recursively. If we were recursively going to do this, what we should do is we should ask my right child what its height is, my left child what its height is. And then I'll take the maximum of those two, because remember, we're taking the distance to the deepest leaf. And then I need to add 1. Well, here it's height 0, max is 0, add 1 is 1. Same thing over here, height 0, add 1 is 1. Now, for both these nodes, node 4 and node 19, the height of our left child and the height of our right child are 0. 0 minus 0 is 0. We are perfectly balanced nodes, and it makes sense. These are balanced nodes. So we have balance factor 0 and balance factor 0. Okay, height 1, balance factor 0 for both these nodes. Now let's look at this node. This is an interesting node here. Again, we can look at our two children, and we'll take the maximum height. In this case, the height of the null node must be -1. Because 0 is the height of a leaf, right? So that's -1. And, well, 1. So the max of that is obviously 1. Add 1 is 2. Okay, that's pretty clear. But then the balance factor, and here's where we definitely need that to be careful about that null node here. The height of the null node, remember we were saying if the height of the leaf is 0, the height of the null node must be -1. Okay, so then we're going to get -1 minus the height of the right node, right? Minus the right node's height. So minus a 1 gives us -2. My balance factor is -2. Now let's just verify for a second that the math will be the same if we did our heights at 1. Okay. Well, if we started our heights at 1, if we did 1-based height, then the height of a null node would be 0. But then the height of this node would be 2. So we would get 0 minus 2 would still be -2. So for the purposes of computing the balance factor, it's not going to matter whether we did 0-based or 1-based. Okay, now foreshadowing, this node here, all our other nodes so far have had balance of 0. This one's telling us we're out of balance, and it's telling us a couple things here. One, again, the magnitude is telling us how much out of balance. This is 2 out of balance. The right-hand side is 2 heavier than the left-hand side, and that, again, pretty easy to see. But then the sign, the minus, is telling us that it's the right, not the left, that is overbalanced. And again, we'll see this here when we get to our top node. The height then is the maximum of our two heights. So in this case 2 plus 1, so we've got height of 3. And again, the balance factor is height on the left, 1, minus height on the right, 2. So 1 minus 2 is minus 1, and that's our balance factor here. Now, going forward, we have to ask ourselves, well, what counts as balance, and what will be too imbalanced for us to allow in our tree? Well, Adison-Velskii-Landis, when they considered this, said, okay, minus 1 and 1, we kind of need to allow a minus 1 or a 1 to have just a little bit of imbalance, like we saw in our example here. This would include a minus 1. Both of these would have minus 1 or plus 1 rather imbalance, since they're left-hand side heavy. On the root node we'd have plus 1. And then actually this node would have a plus 1 as well, and this node would have a minus 1. And we want to allow these structures as considered to be balanced, because there's no structure with 4 nodes that would be balanced in a strict sense. These are all the structures with 4 nodes. Without a structure like this, that's even more imbalanced. There are a few more structures like this that are even more imbalanced, but these are the most balanced structures you can get with 4 nodes, and if we should count those as acceptable structures for our tree. Otherwise, our tree is kind of not a very useful one, and so Adison-Velskii-Landis basically came up with that idea too, saying, all right, we're going to permit this balance factor to reach ranges of 1 and minus 1, but we're never going to permit it to reach range minus 2 or 2. If it does, then we need to fix this. This is where the self-organizing or the self-balancing comes in. We know that just by adding to a tree, we may have got something that looks like this, but then what do we do when we get here? Or maybe removing, maybe we deleted a node, and then we got here. How do we fix this imbalance now that we've got here? Okay, so I think I already mentioned this bit. Our range is going to be minus 1 to 1. If we're out of this, we're going to be out of balance. So to fix this, what we're going to do is we're going to rely on a rotate operation. And let's just take a look at the operation and then verify. The thing that's important about this operation is that it preserves the invariant. We're not going to violate the invariant by doing this operation. And this is a rotate, but what it is a reorganization step that's going to change the organization of our tree. The way I've drawn this tree here, or the way I've considered this tree here, I've drawn circles for my nodes, but then these triangles, why do I have triangles? Well, the triangles here are intended to be subtrees. Okay. Now, also importantly, for this particular diagram, it doesn't matter, but in future diagrams, and it may be important at some point, we're also going to consider that these subtrees are of the same height. Okay, they have the same height. Now remember, if they have the same height, that allows us to compute the balance factor. And if we had computing the balance factors, if we did assume these were all of the same height, then we can see that this node here is 1 more heavy on the right. Then this node would be 1 more heavy on the left. Now, as a result, these would be balanced shapes. These would be balanced shapes, as long as the subtrees down here are also balanced. Okay. We said they were all the same height. We didn't say they were balanced. But assuming they all satisfy the conditions for balance, then these would be balanced shapes. We might not have to fix them at all. But we're just using these shapes to show how the rotation works. It's possible these are not balanced shapes down here, or that they're not all of the same height. Okay. And for the moment, that's what we're going to consider. And if you want to, the simplest case here is consider when all of these triangles are of height, well, -1 if we're doing zero-base height. Basically, if these are all nulls, if there are no trees there whatsoever. Or the second easiest case is imagine they're all just a single node. In which case, blur your eyes at the triangles, just pretend they're circles, and imagine they're all a single node. Okay, so doing the rotate operations, we're going to have 2 possible rotates. And I want to start on this one, performing the rotate left operation. We arrive at this location, but we more precisely we'll say we're doing rotate left on the A. And so we can think of it as rotating left here, because what's going to happen is we're going to rotate towards the left, where the B is going to come up and the A is going to come down. Okay, and we see that here. The B comes up to be the new root, and the A comes down to be the new child of B. So there's sort of a swapping of the parent-child relationship between B and A. And now for the moment, let's just consider the relationship between B and A. If this is a binary search tree, then A must be less than B, because B is on the right-hand side, which means after the rotate, A should be on the left-hand side of B, which is indeed where we've placed it. Okay, this is important, right? We don't want to upset the invariant. So it's still going to be true, since A is less than B, that it's in the right location here. Okay, B used to be the right child, so now A is the left child. Okay, let's look at some of the subtrees and make sure we didn't mess up anything there too. Well, I'm going to start with the easy one. So E here is on the right child of B. That means it's greater than B. Well, we didn't move it. It's still the right child of B. It's still greater than B. Same thing with C. C is to the left of A, and so it must be less than A. Well, it's still the left of A, so it's still less than A. Okay, so both of those, and then the other point I usually make here is in this rotate operation then, I usually say these guys just go for the ride. The E and the C, these subtrees just go along for the ride. They're attached to A and B, but we don't have to do anything with them. So actually, because they're just going along for the ride, what that actually means in the code is we don't need to change those references. We don't touch them. Those ones just stay untouched. The only references we're changing at this point, at least so far, is we have to change this reference from A to B, and then this reference from B to A. Now we'll notice here there's a problem. B used to have a left child. Okay, now let's look closely at D. What's going on with D? Now D is in a special location. Because it's in the right subtree of A, remember everything over here must be greater than A. Okay, everything over here is greater than A. So D is greater than A. All the things in D are greater than A. Okay, but it's also the left child of B. And to be the left child or left subtree of B, that means all the elements in D must be less than B. So that means D, being where it is in this drawing, the subtree that it is, means it must be greater than A and less than B. And since we know that B is greater than A, that means all the numbers D must be between A and B. They're between them. Well, over here, using the same logic, all of the nodes D here must be less than B, and greater than A. So what we actually do here, the middle child, I usually call this D group the middle child. We've got C and we've got E. They just go along for the ride. But the middle child gets swapped out. It gets passed. And it gets passed in sort of the logical way. B needs to free up its left child because that's going to be A. All right, well, A used to have B as its right child, so that becomes free. Well, we'll reattach D there then. So it actually becomes a very natural operation, especially if you practice it a couple times. You realize, oh, we just passed that middle child over. Okay, so this is what we call the rotate left, going from this state here to this state here. And of course, we can go back again by doing rotate right on the B node here, which will bring the B node down. Again, E goes for the ride. The A node comes up, C comes for the ride, and we swap the D back to where it was before. And we call that rotate right. So this is sort of a loop. You can go back and forth here, which is sort of, I guess, useful at one point where we notice maybe doing a rotation is useless, so we undo it. I don't know. We're not actually going to do that in practice, but we might do that as we start investigating it here in a second, and we start looking at some shapes, thinking, okay, what what's going to happen if we perform these operations on these shapes. Okay, and importantly, what about this shape? So I claim here, and let's maybe just practice. It says here we can fix the imbalance in my tree. Now remember, according to our definition, -2 is imbalance. Now -2 means I'm right heavy. Remember the magnitude is telling me I'm heavy, but the sign is telling me which side. +2 means left heavy, -2 means right heavy. So the way to fix something that's right heavy is to rotate it left. And then vice versa, if something's left heavy, we rotate it right. And so what we're going to do here is, in this particular case, there's more than one case, we'll look at them in a second, but in this particular case, the fix, the cure, is let's do a rotate left on this node that's imbalance 16. Okay, so maybe pause if you like, take a second, and just practice, see what the shape is afterwards. And when you're done, unpause. Okay, so if you did practice, see what you got. Now let's see what we're going to do here. Now, what are our nodes here? This is maybe our A and our B node. My 16 is going to come down, right? And the 19 is going to come up. And the 16 will be its new left, which means 17 must be the one that we passed. So when we move over, so again, just going back here, watch as we switch. The 17 moves over to become the new child of the 16. Okay, the 17 moves over to become the new child of the 16. And the 21 just came up for the ride. All right. All right. And again, the other thing we'll notice is the node 21, it just came for the ride. Nothing changes, so we're not going to change its height and its balance factor. That's also going to be true of 17. We pass it over, but nothing happens to it. It just gets a new parent. The nodes that we need to recompute the balance factor and the height on are going to be 16 and 19. And so after the swap, these are the two nodes we need to do reference changes on. And then after we do the reference changes, we update their height and their balance factor. Okay, so let's just verify. So again, the 21 and the 17, I said the height and the balance factor remain unchanged. They're still leaves, they're still 0, zeros. Okay. My 16 though gets, because it's now the lower node, it gets updated first. We're going to rely on the recursive rewinding of our call here to carry out these operations. So at this point, we're going to start back at the 16 here and say, all right, update your height and your balance factor. And it will. So let's check here. My height, my maximum height here is 0 plus 1 is 1. And my balance factor here is going to be -1 on this side minus a 0. So just a -1. That's fine. That's still in the acceptable range. Up to our node 19 now. Again, looking at our two heights, the maximum is 1, so our total height is 2 plus 1. And then the balance factor is 1 minus 0 is 1, again in our acceptable range. And then we will also have to recurse up to calculate the balance factor on the top level, although we'll notice here nothing changes. We still have height of 3 and balance factor of 1 minus 2 is -1. All right, so let's take a look at how we're going to use these rotations now to maintain balance in our AVL tree. Okay, so the first thing we're gonna do is in an AVL tree, when we perform any of our normal operations, our add and our remove in particular, we're just going to perform our normal add and remove as we would perform them in a naive binary search tree, which means we're going to search for the location to add or the node to remove, and then we're going to perform the operation as our add and our remove operations are performed normally. When we do that, we'll notice that only nodes along the path from the root to the node that we are going to be operating on can have a potential change in their height or balance factors. Any other nodes outside of this path have no potential chance of having their height or their balance factors changed. So we only have to be sensitive as we go up. We don't have to go back to every node and see if their height and balance factors change. That's lucky and important, because if we did have to visit every node, of course, that would be order n at the minimum. but we're trying not to be that expensive. We want to be more efficient. So luckily we don't have to. We only have to visit nodes along the path from the root to this node. And remember, we were calling the length of that path already d, the depth of that node. Okay, so far so good. Order of d is not bad. Order of n is bad. Okay, so we only need to change these heights and balance factors along this path. Now the other important thing is we usually want to update the heights and the balance factors lower down in the tree before we update the ones higher up in the tree, because the ones higher up in the tree depend on the ones that are lower down in the tree. Luckily, the way we carry out our adds and our removes in our binary search tree is with a recursive add or a recursive remove. And so these recursive calls allow us to backtrack back up as they unwind. We recurse down as we go down, left, right, and then as the recursive calls unwind, we visit those same nodes on the way back up. So on the way back up, we recompute the height and the balance factor as the recursive algorithm backtracks. Okay. Again, as we're doing that, we might go and we might detect an imbalance, something that's outside of our acceptable range. If we detect that on the way back up, we stop where we are and we correct it right away. Okay, that way no imbalance can accumulate in our tree and can never knock us out of this range. As soon as we get to a -2 or a 2, that's as far as we'll be able to go, because we'll fix it. We'll go back to -1s, 1s, and 0s after that, and therefore we'll never get to states that have 3s or -3s or anything more than that. All right, I say here, if we detect the imbalance, then there's going to be 4 possible cases of imbalance. And these cases have 4 names, pretty straightforward names: right, 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 left, left, right, and left, left. And these 4 different cases, well, the upshot is each case can be solved with at most 2 rotations, but the right, right, and left, right case can be corrected with 1 rotation. We just saw that. The case we looked at was a right, right imbalance, and we used 1 left rotation to fix it. So maybe you can guess here that the left left case can be fixed with a single right rotation. The other 2 cases, the right left and the left right, can be converted into the right right and the left left case respectively. So right left can be converted into right right, and left right can be converted into left left with a single rotation. And then we just fix them with 1 more rotation. And maybe incidentally, as a little bit of fun, you can actually turn a right left into a left right, but it's kind of useless. You can turn these back, these can be turned into each other, but you don't get anywhere by doing that. You might as well just change the right left one into a right right instead of changing it into a left right and then a left left and then fixing it. That's 3 rotations instead of 2. So while you can turn them into each other, there's no point in doing so. It's usually an error if you do that. Okay, so as I said, if we can fix all 4 cases in one of these 2 ways, then in the worst case we do 2 rotations. If we're lucky and get in one of these cases, we only do 1 rotation. The other thing that is maybe important to comment is that each rotation is also only going to do a constant number of reference updates. So you know, even though we might be doing 2 rotations, that's still a constant number. We're still in that realm of only doing a constant amount of extra effort, and that's important. Okay, here are our 4 cases of imbalance stated for us again visually. This will be our left left. You can see it's because our top node here is the one that's imbalanced in all of these cases. Here we are assuming all of our triangles are of the same depth. Again, if you want, just blur your eyes and pretend no triangles are there at all, and then you have depth -1 or 0, depending on which depth you prefer, in which case we would just have 3 nodes, and that's out of balance then. And we get the same thing here. This would be out of balance, but we call this a left-right. Now this is left-left because A is left-heavy, but its left child is also left-heavy, so left-left. Okay. Now notice if you're out of balance, your magnitude has reached 2. You need to have 2 cases of imbalance. You have to be imbalanced, and then one of your children has to be imbalanced too. So in this case, left is telling us that the first left is telling us our left child is heavy, and then the second left is telling us our left child is heavy. So now we have left, right, and again we can change this structure, the left, right structure, into the left, left by doing a rotate left on the B node, and we'll look at an example of that in a second. And then same thing here, we have the same two structures on the right, they're just, you know, symmetric, right, 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 left. Again, we can turn the right, left structure by doing a rotate right on the B node, it will turn us into this structure. The labels are different, I should mention, but if we did a rotate left, or rotate right rather on the B here, we would get something that has this shape with different labels. And then we can fix this shape. So this is the shape we actually saw in our example, which we fixed by doing a rotate left on the A, and then we can fix this one by doing a rotate right on the A. So again, these are our four shapes, and we can actually go back and forth between these two by doing rotates on the A node as well. So I mentioned it might be an error. We know we can fix this state by doing rotate right on the A. If we think we can fix this one by doing rotate right on the A, we get an accident because we do rotate right, but this middle child gets passed over to the B, and we still end up imbalanced on the right side now. So again, practice those. Do rotates on each of these and see where you get. All right, so I mentioned the important rotation. The good one is the one that fixes things. And you can see here it goes from a state with considerable imbalance. Remember, we are assuming all of these have the same depth, so when we get, or same height. So when we get to this state here, all four of them here, since they all have the same height, B is perfectly balanced. So we go from a state where the A is imbalanced to a state where B is perfectly balanced. And what this also means is if this imbalance here would also create imbalance later on up in the tree, fixing it here actually fixes it up in the tree as well. Okay, I mentioned we can change our two shapes. Here I've got the labels actually correct. So we can do a rotate left here on my B. The B will come down, the C comes up. The E and the F go for a ride, but the D here is the middle child that swaps over. Okay, the G completely untouched. All right. That switches us into this state, which is still in balance, but we can now, just going back to the last slide, we're in that state, we can fix it with this one. So from here we can go from this state to this state, and then from this state to this state, and that fixes this imbalanced state in two rotations. Okay, so let's maybe take a look at a couple more examples. Here I wanted to just do some removes instead of adds. We practice adds a lot, but the same kind of imbalance could be created by doing a remove operation. So let's do one. Let's do a remove and see what happens. So I say let's do a remove 4. Now let's remember we're going to do the normal binary search tree remove, which means we're just going to, in this case when I have 2 children, I need to promote a suitable replacement. Now luckily this one I only have 2 children and their leaves. It really just means I get to promote one of them. Whichever one I want actually. If the 3 is promoted here, it's in the right location relative to the 7, and if the 7 is promoted here, it's in the right location relative to the 3. And I can leave it up to you which one you want to do, because when we're done, I did it this way obviously, when we're done, the balance is not upset in this case. So I did, let's just maybe verify for the nodes along the way. The node we deleted, okay, that one had its height and balance factor change. This 3 was untouched, so we don't have to change it. It's still 0, 0. But we do have to update the 7. So we update the 7. It is height 1. Its balance factor will be 1, which is 0 minus -1. Remember the height of the null node here is -1. So minus and minus 1 gives us the +1. So balance factor of 1. And remember that positive sign meaning left heavy. Okay, up one more. Just as the recursion unwinds, we double check here as well. I look at the height of my 2 nodes. 2 plus 1 is 3. Okay, we took the max, and then we do the difference. 1 minus 2 minus 1, we're still good. So actually removing the 4, no imbalance introduced. And that's because we had a pretty nice balanced tree we couldn't introduce any imbalance with a single delete. But with another delete, maybe we can. So I'm going to remove the 7 now. Now removing the 7, remember, this is a node with a single child, we just promote it. So that's pretty straightforward. The 3 gets promoted up. And our height and our balance factor, again, untouched because we just brought it up. But we did change this node, so we need to update its height and balance factor. Its height still remains the same, but its balance factor now, 0 minus 2 is -2. That's out of balance, out of whack. Okay, and as it says here, negative sign means we've got a right blank case, right something, right or right left. How do we know? We need to check the right child. So we'll check the right child. The right child is a 1. Now it should be a 1 or a -1. It's the sign we're really looking at here, not the magnitude. We know it should be out of balance. That's how we got a -2 up here. But how is it a right side out of balance or a left side out of balance? And again here, the positive sign tells us that it's a left out of balance. So the minus sign here gave us the right, the plus sign here gave us the left, so we know where right, left. Or we just look at the shape. But I mean, programmatically, you're not going to be looking at any shape. If you're writing the code, you're looking at the sign. Okay. That means we need 2 rotations. What rotations? Well, hopefully we remember. Well, we want to get this into a right case so we can fix it with a left rotation on the 15. The only way to do that is to fix this left heavy thing and make it a right heavy thing. And we'll do that with a rotate right. So we're going to fix this left first by doing a right, and then we'll fix this right by doing a left. So first rotation, rotate right on the 19. So 19 comes down, 21 for the ride, 16 comes up, 17 over. This was actually undoing the rotation we did earlier. We fixed this problem earlier with a rotate left. Well, we had to undo it now to fix the imbalance that arose up above. Okay, so now we've got some imbalance above here. Remember, we're in the middle of fixing things here, so we're not going to undo this one. That'll just put us back where we were. Okay, now we're in the middle of our 2 rotations. Now we finish off by doing a rotate left on our 15. So the 15 and the 3 goes down for the ride. The 16 is our new root. We pass over the middle child. There's no middle child this time. It's a null child. Okay, so we move it up. Now, in so doing, which nodes did we modify? We modified the 16. Maybe let me just quickly go back. We modified the 16 clearly, but we're also modifying the 15. We're deleting its right child and adding its new left child, which happens to be null. And then the 16 is getting a new left child. So we need to update the height and balance factor of those 2 nodes. All the remaining nodes untouched. So this whole subtree just came along for the ride, untouched. This 3 untouched. And then this node here, again, just let's verify. Height is 1, right? Balance factor is 0 minus a -1 is 1. And then again, this node, height is 2, and then its balance factor, 1 minus 1 is 0. So we're good. So all the balance is corrected. We did 2 rotations there. Now, and that was after removing our 7. Okay. So again, a delete or a remove operation can result in rebalancing. Adds can result in rebalancing, obviously. So we need to be sensitive of that in both operations. Okay, so let's just think about the runtime here. I've sort of been hinting at it as I go along that we are introducing extra work when we process the nodes, but we're only introducing extra work that we in steps where we were already doing work. So while we were doing the add or the remove, the first thing we do would be to recurse down and then unwind back up, while maybe in the naive case, unwinding back up, we don't do anything. We just let the recursive call stack pop off. In this case, we actually stop after each pop and check and say, wait, now that I'm back at this node, revisiting this node again, I have some extra work to do. But what extra work do we have to do? We have to update the height and the balance factor, and then we might have to do some rotations. But both of these steps, as I commented as we were going along there, only do a constant amount of extra effort. And so that means that at each node we do effort on the way down and the way back up, but the amount of effort we spend on each node is still a constant amount. The difference, and maybe the important difference to take away, is that constant has gone up when we're working with AVL trees. And in a naive binary search tree, the constant is pretty small, whereas maybe we've doubled it or tripled it here with the AVL tree, depending on your implementation and the kind of environment you're working in. Okay, but a constant is a constant, which means we've been ignoring them when we translate into big O notation or into big theta notation, which means the cost of our operations is still dominated by that trip down, that recursive trip down. How many nodes do we visit? Because we're doing a constant amount of work at each node, so how many do we visit? Well, we were calling that depth, the depth of the node. Okay, and so again in our AVL trees, we have maintained this. We haven't increased the cost any. What we're hoping to say now, though, is that in our AVL tree, we've got a new promise on the depth. Remember, in our naive binary search tree, the worst case depth could be order n. Yuck, we don't want that. We hope we can get something nice, log n, like a heap. And then, spoilers, that's where we're going to be. Let's see if we can analyze that cost now. Okay, so to analyze the cost, we're going to carry out a task of trying to find the sparsest AVL tree of any particular height. All right, the sparsest AVL tree of any height. Sparsest meaning minimum number of nodes. So let's just try a couple heights. So I don't know, I'm going to go height over here. That's an n, I want an h. So h0, height 0, the sparsest height, or the sparsest tree of height 0 has a single node in it. Okay, so maybe I'll put n over here. So n is how many nodes I was able to fit in there. So let's say I got height 1 now. Now, let's do a couple cases here. I want to be careful. This is not the sparsest node. This is a full tree, remember. Okay, so the full tree is not the sparsest. That's the sparsest. Okay, I can't delete this node here because then I get to this tree and I'm down to height 0. So the number of nodes I can keep in this tree, height 1, is 2. Height 2. And maybe we tried some things, here's one. We did a couple of these already. Here's one, right? And all those weird imbalanced shapes. These are all balanced, remember. We couldn't do this one. That doesn't satisfy the AVL tree because it has too much imbalance. But these ones, and there's the other two mirror images of them. These ones counted as balanced. And we don't want to add more nodes here because then it's not the sparsest, right? These were the sparsest. This was sort of our sparsest image. And in fact, what we can actually start doing here is we realize if I want to make the sparsest one of size 3, sorry, not size 3, of height 2, what I need to do is I'm going to pick a new node, and on the left-hand side, I'm going to take the sparsest one of height 0. And then on the right-hand side, I'm going to do the sparsest one of height 1. Now what I've done is I've guaranteed the height on this side is 0 and the height on this side is 1. So I've guaranteed my AVL tree is satisfied for this node. And then by picking trees that I've already built earlier on, I know those ones already satisfy the AVL definition. So this is the sparsest one I can put of size 0 that actually satisfies AVL. This is the sparsest one of height 1 that actually satisfies AVL. So I'm going to make that my tree here. This is my tree of height 2, and let's see, boom, 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 it's got 4. Okay, now I'm trying to find a pattern in n, and you can work with me here. If you figure it out, you can stop and fast forward. I think this pattern's a little tricky, so I want to keep going here. Okay. Now let's recursively do what I said again. If I want one of height 3, I'm going to put one on the left and one on the right. So again, I'm going to make a new root node. On the left-hand side, I'm going to pick one of height 1. So that's this tree. I'm just copying this tree out and copying it here. On my right-hand side, I'm going to copy out this tree. Okay, so again, ugly, but this is my sparsest tree. Now there are other trees, AVL trees. You know, I could flip this over to the other side or flip this around a little, you know, swap the left and right child here. These would all still be legal ones. They would be different trees, but they would still have the same number of nodes. And how many? We got 4, 7, looks like. Okay, I want to go one more. To go one more, I'm going to cheat a little bit here. I'm going to do, this was the one we had before, and then I can do this. This is my next one. Maybe I'm running out of space, so too bad. This is it. I guess I need to know my pattern after this one since I ran out of space. We had here, and then what? This one was, whoa, it had this. Okay. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 nodes. Any pattern coming out here yet? I don't know. But one thing I've noticed is, how did I build this tree? Okay. I'm gonna give this column a name. I haven't called it a name yet. Let's call it T for tree sub H. Okay. So what I did when I had trees to make the new tree sub H, what did I do when I made tree sub 4? I made a new node. Maybe I'm just gonna count numbers here. So actually I'm gonna count size. Right? If I put the bars on the outside here, I mean how many nodes in tree sub H. So this one, n, is the size, of tree sub H. Okay. So here I'm saying tree sub H, how many nodes are in it? How did I build it? Well, I took one new node, and then I added the whole tree of one size smaller. That's actually this one on the right. And then I also had one of 2 sizes smaller. Okay. And let's just make sure that this is true. Let's see here. 12 is equal to 7. So that would be 7. And 4 plus 1 is indeed 12. So we've got it right. Let's check again. 2 plus 4 is 6, plus 1 more is 7. 1 plus 2 plus 1 more is 4. So 7 plus 12 is 19. The next one should have 20 in it. And the next one, 12 plus 20 is 32, should have 33 in it. I feel like we found a pattern. And the way we found the pattern was by identifying this recursive relationship that we have here. And how did we identify that recursive relationship? Was we started adopting a recursive algorithm to build our trees. Okay, let's follow through this idea a little bit further. So we wanted to come up with the sparsest AVL tree of size H, and kind of what we were trying to figure out was how many elements there were in that tree. So here's again this was the recursive structure we did. We said take one new node, put the tree of height 2 smaller on the left hand side, of the height 1 smaller on the right hand side, and this should be the minimum height tree as long as these two were not minimum height tree, sort of sparsest tree, minimum nodes tree for that height. Okay, so continuing, we did that. We came up with this recursive sequence, and in fact, I didn't mention this, but this is actually very similar to the Fibonacci sequence. Remember, the Fibonacci sequence says Fibonacci number n is equal to the last one plus the one before. None of this plus 1 business in here, but we're obviously very closely related. Okay, so hey, these were the trees we just built. Okay, we could call these tree 1, 2, 3 up to 5 if we wanted. Okay, and we also calculated these values, and in fact we can write these values down. We got a few more of these here, and if we write them down and we compare them to the Fibonacci numbers, they're actually really closely related, and I've just lined them up here sort of so we can see that they're actually one less than a Fibonacci number, and we're just a little bit out of sync. And maybe with a little bit of relabeling our h's here, we can make them come in sync a little better. But we can see they're just a little bit out of sync. They're just one less than a Fibonacci number. Okay. So what, maybe we're losing track of where we're at. We're jumping around here. We're talking about these trees, okay? And say we had a tree of height h, and we want to know what is the minimum number of nodes we can put in that tree. We already know what the maximum number is. We looked at this in a previous video, but let's just revisit it here. The maximum number of nodes we can have in an AVL tree of a certain height is just however many we could put in a complete binary tree of size of that depth. So here we've been talking about height, right, h. So if we had a height here, some height tree, our maximum was 2 to the next height minus 1. That value we already calculated for our complete binary trees, but in particular for our heaps as well when we were using them. We use a d there maybe instead, but it's the same principle. So we know what the max is. Remember, this is the maximum number of nodes we can put in there. Max n. We usually use n for number of nodes. But now we were asking, what's the minimum number of nodes we can fit in a tree of size h? Now, this is a simple question if we're not talking about AVL trees, right? It's h, right? Or, h plus 1, h minus 1 if you're off a little bit with your calculation. But it's order h, big O of h at the very least. Okay. But we're saying with AVL trees, maybe that's not true. So in our investigation, this is not a legal AVL tree because it's imbalanced. So assuming we enforce balance, this is a legal AVL tree of depth 5 that has as much imbalance as we can put in it as possible, which means we took out as many nodes as we could. We could think of starting with the complete tree. How many would the complete tree have? Okay, so again, 0, 1, 2, 3, 4, it would be the next one up 5, okay, which would be 31 nodes we could fit in this tree. But we got one here with only 20 nodes in it that satisfies the AVL definition. So again, our question that we're kind of asking ourselves is, how many nodes on the minimum can we assume we have in an AVL tree if we know its height? And so here we've come up with that calculation. And the weird thing we found out is it's a Fibonacci number. The number is a Fibonacci number, well, minus 1. Okay. Okay. So we can kind of come up with this translation if you want. All right. And if you want, ignore the minus 1. That's not really relevant. Okay. Let's complete with a little bit more discussion of Fibonacci. If you're interested, I recently posted another video in a different series related to the Fibonacci sequence, where I go in a lot more details about the sequence and how we might use it in an algorithms context. But one thing I talk about here is the ratio of the Fibonacci sequence, Fibonacci n over Fibonacci n over Fibonacci n minus 1. If you take the limit of that as it approaches infinity, you get this special number here. It's called the golden ratio. Some of you might know what it is. And the golden ratio is actually an approximation on the nth Fibonacci number. So if you want to know what the nth Fibonacci number is, you can take this number 1.618 and so on, or more precisely 1 plus root 5 over 2, raise it to the power n, and that's going to give you pretty close to the nth Fibonacci number, which gives you a way of calculating the nth Fibonacci number a little bit quicker than other ways. Again, take a look at my other video if you're interested in calculating Fibonacci numbers. We're just looking at the Fibonacci numbers for the purpose of understanding our AVL tree. And so what this tells us is, remember, we were looking at how many nodes, n, could we fit in our tree of size h. This was the minimum AVL tree of size h. And we found out that it was this formula, Fibonacci number h plus 1 minus 1. Again, ignore the minus 1, not very important. And then we just argued here that a good approximation on that Fibonacci number, if we want, is this exponential function. So n here, the number of nodes, is going to be something like phi, we call this number phi, this is the Greek symbol phi, to the power h plus 1 minus 1. This is exponential. Hey, that's okay, that's pretty good. Okay, remember when we were talking about the number of nodes of depth d for a complete binary search tree, this was 2 to the d plus 1 minus 1. Phi is smaller than 2, so this is smaller. This value is smaller than 2 to the h plus 1 minus 1. Okay, and again, we want to know what h is, or we want to know, let's turn that around again. We know what h is, so this will tell us how many nodes we can put in there. But now say we know how many nodes there are, we want to predict our depth, or the height. So say someone comes to us now and says, hey, I've got an AVL tree. It's got 1,000 nodes in it. What depth should I expect it to have? What is my depth limit or my height limit? What's my prediction on its depth? So inverting this, we're going to take the log of both sides here. Log base phi, actually, log base phi. That's going to cancel us out and make things a little bit easier for us. Okay, a little bit of extra algebra, ones go around, but if you want, ignore the ones that are not as important as the fact that h here is log base phi of n. And converting that log base phi of n into a log that we like, usually log base 2 of n, pops out a constant here. Now again, normally that constant we don't care if we go to thetas, and in a second we're going to big O's and thetas, and that's going to disappear. But let's consider two cases. So let's say we had a heap, okay, and let's say it had 1,020, I'm going to be careful here, 3 nodes in it. Okay, so we know that that's enough to perfectly fit in a heap of 0 up to 9. If we had node 1024, it would go right here. Okay, so in this heap of 1023, we know that the depth here is 9 if we went 0 based, or maybe I'll just say /10 if we went 1 based. Okay. Now, what we're saying here is that for our AVL now, same business. Maybe we have 1,023 nodes in there. Okay. But our AVL tree is not promised to be perfectly balanced like this. Remember, this is perfectly balanced. This is every node on that last row is filled in if we have 1023. So it's possible our AVL tree pops out perfectly balanced. We'd be lucky. It's possible, but it's unlikely. Okay? There's more likely that we're a little bit imbalanced. So what balance could we expect? Now I'm going to use the 1 base calculation here because it makes our math a little better. We don't have to mess with the plus and minus 1s as much. But it's here where this 1.44 is going to show up. Okay, remember this 1.44 times log base 2 of n. Now the log base 2 of n here is our 10, right? Okay, so this is what, 14.4? So what that's telling us for our AVL tree then is if we have 1023 nodes in it, then we know that it's bounded above at least by this. This is its height. Okay, we're guaranteed its height is bounded above by this. All right, which means it's still in log n, which is important for our asymptotics, but it also gives us a numerical value that we can compute if we want to. Okay, so our heap with that many nodes is nice and squat with 10. Our AVL tree, not quite so squat, but still pretty squat. 14.4, pretty good. Why am I saying pretty good? Well, what's the worst case? What was just our normal binary search tree? Not an AVL, one that doesn't rebalance itself. Well, on average, it might be small and down to a log n, but remember, we could get that really bad long one that looks like this, right? How long is that one going to be? 1,023 long. So how does 14.4 compare to 1,023? Really good. That sounds really good. How does it compare to 10? Looks almost the same as 10 compared to 1023. They're very close. Okay, and indeed that's the case. Our AVL tree does have this nice performance. It maintains this logarithmic runtime, and so we feel it's efficient in the performance of its operations. And let's just conclude then that we've shown that the maximum depth of our AVL tree is going to be order of log n, where n is the number of nodes in the tree, which means since earlier in our earlier slide we said the cost of our search, our add, and our remove are the depth of the node that we are searching for adding or removing, and secondly, the depth of the node we're searching for adding and removing is upper bounded by the depth of the whole tree. And since the depth of the tree is log n, the depth of all these nodes must be log n, and the depth of all these operations, or the cost of all these operations, must also be log n as well. Okay, so that's one of the benefits of the self-organizing or self-balancing binary search tree, is that it maintains its balance, and in so doing maintains a nice logarithmic depth. And by maintaining a nice logarithmic depth, guarantee efficient runtime for the important operations, the search, the add, and the remove. Okay, one takeaway from this, this isn't the only self-balancing binary search tree. It's a fairly simple one to understand. And in our next couple videos, in the next video I think I want to practice with AVL trees a little bit more. We only just looked at them here. But in the follow-up video to that, I want to look at red-black videos, or red-black trees, sorry. And the red-black tree is another self-balancing binary search tree that uses different rules and has a different definition for balance, and as we'll see, has a trade-off to AVL trees, and so you might use that trade-off to decide which one you might want to use. All right, well, thanks for watching this video, and we'll see you in the next video.